Hey guys, welcome to the function section of the grade 12 November 2024 Mathematics Paper 1 exam. Okay, so this is question 4, and question 4 says, given f of x is equal to a to the power of x minus 1. So we have an exponential function over there, and a is greater than 0. And then they tell us that b is a point on f. Calculate the value of a. Okay, simple. You can see that a is the only thing missing in the function. So if f of x is equal to a to the power of x minus 1 and b is a point on this graph, then you can substitute this into this function. So this is the x value and that is the y value. So we can substitute as negative 5 over 9 is equal to a to the power of, and in place of x we'll put in 2 and then minus 1. So there we go. We've put our y and our x value. And now you see that we can actually use this to solve for a. Okay, so let's go ahead and take negative 1 over. When negative 1 goes over, it becomes positive 1. But here's the thing about positive 1. It can be written as, because this denominator is 9, I'll write it as 9 over 9. You can use a calculator. And then it's minus 5 over 9 is equal to a squared. And 9 minus 5 is 4. So this is 4 over 9. The denominator stays the same since we're subtracting. And we have a squared. Okay, so this is actually a quadratic equation. So to solve for this, to get a alone, the 2 is disturbing us. So we need to get rid of the square by square rooting both sides. So with equations, you need to remember that plus or minus. And therefore, a is equal to, but here's the thing, they say that a is greater than 0. So you don't have to take the negative 1, of course, because it's exponential. So that is going to be 2 over 3. So a is 2 over 3. Okay, moving on to the next question. The next question says, write down the range of f. Okay, and this is just for 1 mark. So now that we have a, it means that your graph looks like this. F of x is equal to, and you just have 2 over 3 raised to the power of x minus 1. So remember that the range is all the possible y values of the graph. When you're looking at this graph, a rough sketch on what it's going to look like is you see that you have 2 over 3. And I would actually want to explain this more when we're sketching the graph. But the thing is that you need to focus on what is in front of this 2 over 3. You see, I know that they call this a, but really this 2 over 3 is a base. So you know in your exponential equation or function that says a times b to the power of x minus p plus q. That b, that's the base here. Okay, that the a is the coefficient of that base. Now, what is that number right now? It's actually an invisible 1. So we can agree that it's positive. When your graph is positive, regardless of how it looks, whether it is increasing or decreasing, it will lie above the asymptote. So the asymptote here would be y is equal to, as you can see, you have a negative 1 there. That is the horizontal asymptote. So this means that this graph, all the y values it will have will be values that are greater than negative 1, because you'll have negative 1 on the y-axis. And then you don't have any graph below negative 1, only above. So all these parts of the graph, they're going to be above negative 1. So our answer here is simply just that y is greater than negative 1, not equal to negative 1, because the asymptote is a line that the graph will never touch. So negative 1 is not included there. Okay, and that is the answer for that question. Moving on to the next question. The next question, 4.3, says, sketch the graph of f, clearly show the intercepts with the axes and the asymptotes, if any. Okay, so let's go ahead and see, what do we need in order to sketch this graph? It is an exponential function. So here are the things that we can look at. First of all, we can look at the shape of the graph. Now, when I'm referring to the shape of the graph, I'm really speaking about where it is. First of all, is it above or below the asymptote? Is it increasing or decreasing? Okay, so when we look at this graph, we know, first of all, it is definitely above the asymptote because of the a value being greater than 0. But is this graph increasing or decreasing? Look at this part of the graph. So just this part with the exponent. It's 2 over 3 to the power of x. what happens with 2 over 3 to the power of x? The way you can just test whether a graph is increasing or decreasing, take that part that has the base, right? And substitute two values in it. Substitute x is equal to 1 and substitute x is equal to 2. Because you're supposed to read graphs moving from the left to the right. That's why I'm looking at a value like 1 and 2, because I want to see what it's doing. When you substitute x is equal to 1, you know that an exponent of 1 doesn't change anything. So you'll still have the 2 over 3, meaning you have 1, and let's just say this is 1 here. So you would have 2 over 3, which is round about here. Then what happens when you substitute 2? Well, the 2 gets squared, the 3 gets squared, and you get 4 over 9. Now you'd have to see between 2 over 3 and 4 over 9, which one is bigger? As a decimal on your calculator, you could check 2 over 3 is like 0.6 recurring. Then what is 4 over 9? 4 over 9 is 0.4 recurring. So you can clearly see now that the 2 over 3 is bigger. So what does that mean that this graph is actually doing? This one got a bigger y value than this one. So this graph is generally decreasing. Okay, so that's just an easy way to put it. It's generally decreasing. But really the idea behind it is what you have as a base here is a proper fraction. And a proper fraction will always have the numerator being bigger than the denominator. Because you have an exponent, these numbers are going to grow. But the thing is, because the denominator is bigger than the numerator, it's going to grow more than the numerator. So it's always going to be bigger than the numerator, therefore making the fraction smaller, and just gets smaller and smaller as it progresses. Okay, so that is one thing you guys need to really look at. Okay, so we know that the shape of the graph, it is a decreasing function that lies above its asymptote. Okay, so first of all, we know it looks like that. Then the next thing that we can look for, well, we have a point on the graph, that's good, but we can go ahead and look for an x or y intercept. Let's go ahead and start with the x-intercept. So to find an x-intercept, you need to make y equal to 0. So our graph looks like that. Let's make y equal to 0. So that is 0 is equal to 2 over 3 to the power of x minus 1. And now that we have this, we can solve. So take the negative 1 over, it becomes positive, raised to the power of x, and you have 1 is equal to this, right? Remember, you have to make the bases the same because right now this is an exponential equation. So to make 1 a base of that, it's 2 over 3 to the power of 0, because anything to the power of 0 is 1. And now you see that our bases are the same, and therefore we can equate the exponents. So x is equal to 0. What that point is 0, and remember we already made the y value 0. With that being said, you don't have to look for a y-intercept because this graph is going to pass 0 and 0. Remember, the x-intercept is where y is equal to 0, and the y-intercept is where x is equal to 0. Your x is already 0 here, so that means that your x and your y-intercept are at the same point. So we don't have to look for a y-intercept in this case. It's actually just 0 and 0 as well. Okay, so that's all we need, and now we can just sketch our graph. So you don't have to be too fancy with your graph. It doesn't even need coordinates too much. You don't really need stuff here. So just label, this is my x and this is my y. The first thing and the most important thing to do is first put down your asymptote. So your asymptote is -1, right? That's your horizontal asymptote. So we're going to put that down here. So let's just say it's here. And then it's of course going to be a dotted line. So that is y is equal to -1. So we have that down. And we can also just put down any points that we have. We have the x and y intercepts that are being shared at 0 and 0. So that's over there. And then another point that we have, just in case it's important, we'll put it down B. Okay, so we'll just give a rough estimate of where that would be. 2 and -5 over 9. So +2 and -5 over 9. So it's down, but it's not touching the asymptote. And you can just label that B. And of course, put the points down. So 2 and -5 over 9. And then you have to draw your graph. Remember that your graph is a decreasing function. We saw that. So it's going to go up like this and then down and connect and move like that, but never touch the asymptote. Okay, so there we go. That is our graph of f. And we can just call it f. And there we go. That is done. Moving on to the next question. The next question, and really the last question for question 4 is, It is further given that C is a point on F at y is equal to 19 over 8. Okay, so there's a point on F and it's called C. Determine the coordinates of C prime, the image of C. So C prime, when C is reflected about the line y is equal to x. Okay, so this is textbook knowledge. You need to understand what it means for a graph to be reflected about a line y is equal to x. The line y is equal to x is that line that is perfectly diagonal. Okay, y is equal to x because every single point is really just repeating itself on the x and the y value. Okay, so you'll have 1 and 1, 2 and 2, 3 and 3, 4 and 4, and so on. Now this line, if you reflect anything across this line, in this case we have a decreasing exponential. If you reflect it across this line, the reflection will be the inverse function. Okay, so now that we know that C is just the original and C prime is the inverse, you also have to understand the relationship between the original function and the coordinates there and the reflection. You see, if you have an original function and it has x and y, the reflection, all that happens, the reflection across the y is equal to x. In other words, the inverse, what happens there is the x and y value swap. Remember when you had straight lines and they'll tell you find the inverse function of this, then the first step would be swap x and y. Well, that's actually what happens with all the coordinates. The x and y values swap. So that would go here and that would go here. They just switch places. So let's look at what we have. They told us that C, right, is a point on the graph of F at y is equal to 19 over 8. So they didn't tell us what the x value is, but they told us what the y value is. So since we know the y value is 19 over 8, clearly we only need the x value. And once we find the x value, we will know that we'll just switch these around and that would be the inverse's coordinates. Okay, so let's go ahead and do that. First step is find the x value of the original on the original function. So to find the x value, why don't you just substitute the y value in? We already have the function, right? The full, that is it. Okay, f of x is equal to this. And we're just going to substitute that y value so that we can find out what exactly the x value is. So substitute the y value. Now we're going to have there 19 over 8 is equal to, and we have 2 over 3 raised to the power of x minus 1. And let's go ahead and just solve for x. So to solve for x, we can take the 1 over. That really just becomes a positive 1, which we can write as 8 over 8. See, I'm trying to do that because the denominator is 8. And it's plus 19 over 8, because that's positive, is equal to 2 over 3 raised to the power of x. And so 19 plus 8 is 27. So we have 27 over 8 is equal to 2 over 3 to the power of x. Okay, so this is something we can solve. Yeah, it looked like we could actually just make the bases the same, but I can see that we can't. If the denominator was 27 and the numerator was 8, then you could have done that. So in this case, I would advise that you just use log. Okay, that's the best thing to use here. So log makes the exponent the subject. So we make the exponent the subject and we say log of our base. So our base is whatever was carrying the exponent, which is 2 over 3. And then the answer we put here, so 27 over 8. Okay, so let's just go ahead and find out what exactly that would give us. On your calculator, make sure to use that log, the one with the base. Okay, so 2 over 3 and then 27 over 8. And we get, okay, so we get negative 3. Good. You get a nice solid number, negative 3. And so now that we know the x value is negative 3, what it means is that C is negative 3 and 19 over 8. And so C prime is going to be 19 over 8 and negative 3 because they just switch places. And that is your coordinate for C prime. Okay, so that is it for that question. And we move on to question 5. Question 5 says, sketch below is the graph of f of x is equal to, and this is a hyperbola. But the thing about this hyperbola is it's not in its original format. Remember that the original format is this. So they're clearly just trying to make you think a little more there. And then they say having the domain where we have, Okay, so it's going from negative infinity to 1 and then union 1 to positive infinity. So they just chose a different way to write it, but it's really ultimately saying that you're going from negative infinity, so negative, infinity, and then you're going all the way to 1, meaning there's an asymptote there. And then after that, they're going from 1 to positive infinity. It's really just exactly what is here. The only difference is, do you see that we have round brackets, especially by the 1? So they are showing you that 1 is not included. X is not equal to 1. That's really what they're saying there. And then they say the graph of f cuts the y-axis at 0 and 1. So, okay, that's a y-intercept. And then we have a line of symmetry of f, okay, is given by g of x equal to x minus 3. That is very helpful. So they already gave us an axis of symmetry, okay, for this hyperbola, and that is g. And we have the equation. Okay, the first question is to write down the value of p. Where is p? Okay, so p is this value. Okay, so this is where you really need to think about that. Remember, the original function is supposed to look like that, where you have x minus p. Okay, you know that the vertical asymptote is what we call p. So if that is x is equal to 1, right, positive 1, when you have it in the function, what is that supposed to look like? It's supposed to be a over x minus 1. Okay, that's why it's supposed to look like that. And then, of course, whatever the q is. So now compare what it's supposed to look like with what they presented you with. And now what does that mean about p? What is p? P is actually equal to negative 1 because we have x plus p. Okay, if you're substituting p as negative 1, you're saying plus negative 1, which ultimately becomes x minus 1. And that's exactly what it's supposed to look like. So p has to be equal to negative 1 for that to happen. Okay, so that is the value of p. The p is equal to negative 1, not positive 1. Okay, don't get confused by that. Okay, so that is it for the first question. Moving on to the next question. 5.2 says determine the equation of the horizontal asymptote of f. So this one is what we need to find now. Okay, is there any hint that helps us to find the horizontal asymptote? So you see that they gave you this point 1, 0, and 1, but you can't really just substitute it to find that horizontal asymptote. It won't work because right now A is still missing. So you have A and Q missing. So 1 point is not enough. Okay, so what other thing did they give us? Well, they told us about the line of symmetry, which is a very good piece of information that we can use. Because the thing about the line of symmetry, do you see that it also passes your asymptotes? Meaning here at this point, the x value is 1 and the y value is whatever the horizontal asymptote is, that y value. So how do we find it? Since this is 1 and whatever that y value of the horizontal asymptote is, why don't you just substitute the x value of 1 into the equation of g? And that will give you the y value that we're looking for, that y value. Okay, so let's go ahead and do that. So I already have g of x, so I'll just say g of 1. We're substituting 1 in place of x, and it's x minus 3. So that's 1 minus 3, which gives you negative 2. So now we know it is negative 2, and so that would mean that the equation is y equals negative 2. And there we go. So y is equal to negative 2. Moving on to the next question. The next question, 5.3, says calculate the value of a. Okay, we have P, we have Q, only A is missing. So all we need is a point on the graph. So f of x is equal to A over x minus 1 minus 2, because we have that horizontal asymptote. And now you just need to substitute a point, because if you have a y value and an x value, only A will be missing, and we can use that to solve for A. The only point they gave us on this graph was this 0 and 1. So we can go ahead and use that. So substituting 0 and 1 in place of x and y. So that means we have 1 is equal to A over 0 minus 1 minus 2. Okay, let's take the negative 2 over. It becomes a positive 2, and you still have a plus 1 there, which gives you 3 is equal to And a over 0 minus 1 is negative 1. So that is a over negative 1, which a divided by negative 1 is negative a. Okay, so the a is there. You can just multiply both sides by negative to get rid of that negative, and therefore positive a is equal to negative 3. There we go. So a is equal to negative 3. Moving on to the next question. The next question, 5.4, says, for which values of x is f of x greater or equal to 0? Let's look at that. Where is f of x greater or equal to 0? So this is our graph of f. You see that this wing over here, yeah, that's not greater or equal to 0 in any way. It's not even greater than 0. When they say greater or equal to 0, they're referring to the y values of the graph. So if you look at the points on this graph, right, look at the y values. That's a negative y value. That's a negative y value. That's negative. It's negative all through here. So we can't even use that wing. It's not greater or equal to 0. But when we look at this part of the graph, see that over here, look at these. Look at the point here. Look at the y value there. It's a negative, it's not negative 2, but it's negative something. And then that's negative, and that's negative. And then what happens? Once you get to this point over here, the x-intercept, what is the y value at this point? It is 0. And then after that, you see this line over here, what are the y values here? They are all positive y values, okay? Over here as well. These points have positive y values. They're in the positive part of the y-axis. So these places are all the places with values that are greater than or equal to 0. So the first most important point, the key point here, would be at that x-intercept, because before the x-intercept, everything was negative. So we need to find exactly what that x-intercept is. So find the x-intercept of the graph of f first. Trying to find that. So we'll just put down our graph first. So it is negative 3 over x minus 1 minus 2. And then to find the x-intercept, you make y equal to 0. So that becomes 0 is equal to negative 3 over x minus 2, minus 1, sorry, minus 2. And then we can just take this over instead, so that it just becomes positive. So that's 3 over x minus 1 is equal to negative 2. And then we can cross multiply to get this, the x on its own. So we're going to multiply here. But you see that you're multiplying with two terms. So the negative 2 must multiply to the x, giving you negative 2x, and multiply to the negative 1, giving you positive 2, is equal to 3. Okay, so because the 3 is just multiplying by a 1 here. Okay, and now we can just take that negative 2 over. I should have left it the other way. And this is equal to 2, positive 2 still here. And then the 3 comes over and becomes a negative 3. 2 minus 3 is negative 1. So divide both sides by 2. And therefore, that means that x is equal to negative a half. Okay, we've got our key point. That's what we needed. And we can see if this is a half over here, negative a half, then the values of x for which this graph is going to have values greater or equal to 0, first of all, will be at negative a half. And then do you see, we're just trying to look at the x values now. Do you see that the x values here always line it down to the x-axis? So highlight the point of the graph, the part of the graph that you found is correct, and then line it down to the x-axis so that you can understand which x values it's referring to. So that would be values starting at negative 1 over 2, and then its values that are greater than negative 1 over 2. And you see that they will not go past 1 because there's an asymptote there. So how we can actually say that it's greater than negative 1 over 2, but it's less than 1. Okay, so we can write that as x is greater than, but not just greater or equal to negative 1 over 2, because at negative 1 over 2, your y value is 0, but less than 1. And that will be our answer over there. Okay, so we can just put that down. Our answer is x is greater than or equal to negative 1 over 2, but less than 1. Okay, moving on to the next question. Question 5.5 says, graph f undergoes a transformation. We don't know what happened to it. We don't know if it gets shifted up, down, or reflected, but it undergoes a transformation to h. So it becomes h. Then they tell us where the domain and range of H are the same as that of F. So sure, it gets transformed from F to H, but the domain and range don't change. Okay, that is an interesting point. Domain and range stay exactly the same. And then they tell us that H prime, okay, so that is the derivative, aka the gradient. Okay, so that's another thing you need to remember when you see things about the derivative. They're really just speaking about the gradient of that function. Okay, so the gradient of the function is negative on its domain. So they're saying it's negative for the x values. Okay, let's actually speak about the first point first. Okay, so the domain and the range have to be exactly the same of H and F. Let's look at our graph. I'll really just bring the graph down and let's actually look at that. Okay, so them saying the domain and the range don't change just really means that it's going to stay exactly what it is. Okay, so it doesn't change. Doesn't mean the graph is just going to look like that, but the domain and range stays exactly. So if this starts at a specific point and ends at a specific point, then that's what this transform graph is also going to do on the domain and the range. Okay, how can we actually get that? Can we transform this graph so that that never changes? You see, the thing about this is if you try to shift the graph, that's not very helpful because the domain will change. Okay, if you shift it up, for example, what you're also doing is taking your asymptote and shifting it up. So it's not going to work. So shifting it, up or down or left or right is not very helpful because it's going to change the domain and the range or either one of it. Okay, so shift it up or down, it's going to change that horizontal asymptote, which changes your range at the end of the day. So that's not a good idea to shift it. How else? What other types of transformations are there? Well, there are reflections. So can we reflect this? Okay, so looking at this, it can be reflected across, for example, the y-axis or x-axis. If it gets reflected across that axis, all it does is that it becomes a mirror image of whatever it was. So you see, it looks like this here. It would really just do this. I would love to do that, but that's actually going to change the domain. Here's the reason. If you reflect it, what happens is that you're reflecting across the y-axis. If you are reflecting it across the y-axis, all your x values will change. If this looks like this now, your asymptote is going to be here. So see how that's not helpful? That will end up changing the domain because this is an x value. It changes the domain because this is the vertical asymptote. Okay, it's a very important point in the domain. Normally, we would say, okay, the domain of this is x is an element of all real numbers, but x should not be equal to 1. What will happen if you decide to change it is that the red graph's domain is now going to be x is an element of all real numbers, but x should not be equal to -1, because that's what's going to happen here. That is going to become -1. So that changes the domain. We don't want that to happen. We want the range and the domain to stay the same. So how else can we actually transform this? Okay, so I'm thinking of another way. Another way that you can actually do this is actually two ways. It's not just one way that we have. There's two ways to do this. You can decide to actually reflect this, but not across the y-axis because it changes too much. You can reflect it across this vertical asymptote. You can also reflect it across the horizontal asymptote. So what happens is if we're looking at this line as the line that we're going to reflect it across, this graph is really forming a mirror image here. So this, it gets reflected. You see how this point over here is this far away from this asymptote? Well, the reflected one is also going to be as far away. They are going to be the same distance apart. So you're going to have that point over there. Over here, for example, right? The distance between the graph and this line is going to be exactly the same as your new graph and this line. And then here as well. So that ends up creating a graph that is reflected like that. But the good thing about that is that the domain will not change. The domain is exactly the same because it's still never going to pass 1. Neither is it going to pass -2. Okay, so that is a good way to do that. So of course that would happen to both wings, also this side as well. The way we have that going like that, if it gets reflected across the line x is equal to 1, it's also just going to do this. Okay, and like that. So that's basically what's going to happen. So there's two ways that you can do this. The first way is you can reflect f across the line x is equal to 1. The second way is that you can reflect f across the line y is equal to negative 2. Because the thing is, you see, the thing about a hyperbola is that it's really just symmetrical. If you find, okay, we have the axis of symmetry. You see, we have this one. But if you do the negative one, you will notice that what it does here, it does the exact same thing here. And that's why that's called the line of symmetry, because it's going to cut it symmetrically. So if you reflected it across the line y is equal to negative 2, that's actually what's going to happen as well. As far as, because this is the line of reflection, you see the distance between the graph and this line is going to be exactly the same as the distance between this new graph and that line. So that's why I say you can actually reflect it in through that line x is equal to 1 or through the line y is equal to negative 2, and that will work perfectly. Okay, so that will maintain that. Now, what do they mean by this? H prime, the derivative, is also negative on its domain. Let's actually check whether that's true or not. Is the gradient negative? Here's how you can find out where the gradient is positive and where it's negative. When you see derivative, it means gradient. What gradient really means to be positive or negative is this. If a gradient is positive, it means that your graph is going to be generally increasing. Okay, so it's going to be moving up. And you always read graphs moving from the left-hand side to the right-hand side. If your gradient is negative, your graph is going to be decreasing. So they told us that the derivative, it should be negative on its domain. So our gradient, this graph really just needs to be decreasing through the domain. So when we're looking at the domain, they just mean the x-axis really, or all the x values. Is it decreasing? Yes, look at what it's doing. This graph is decreasing. Look, reading from left to right, it is moving down. Reading again from left to right, it is moving down. So that perfectly fits what we are speaking about. So those are your two answers. You can use either that or that and it should be fine. Okay, so that's an extended explanation. Remember, on this channel, I don't like to do quick explanations because if I explain something and you don't understand, I see that there's no use of you even watching it because you just saw me do it, but then you won't understand what I did. Neither would you be able to actually do the same thing in an exam setting if that same type of question was asked. Okay. And I also encourage you guys to ask questions in the comment section. If anything doesn't make sense, also just point out things. If you see anything that didn't, make sense, because I'm human, I can also make mistakes. Okay, so that is it for that question. And we finally move on to question 6. We are now on question 6, and question 6 says, in the diagram below, the graphs of f of x is equal to, and as you can see, it's a concave down parabola, and g, which is a straight line, are drawn. Then they tell us that c, which is 3 and 8, is a point of intersection of f and g. Okay, so there. Then EH is drawn parallel to the y-axis with E a point on F and H a point on G. Okay, so that's what we have. And the first question is, calculate the coordinates of B, the turning point of F. Okay, so just find the turning points. But as you can see, the graph of F is in standard form. So finding the turning point in standard form. Okay, so how we find the turning point in standard form is, since our equation is f of x, and just leave this as black, f of x is equal to negative x squared plus 4x plus 5. You can use this formula. Okay, the turning point formula is to find the x value is x is equal to negative b over 2a. So substitute your b and your a value. Your a value, as you can see, is negative 1, and your b value is the 4 that we have there. So x is equal to negative and b is 4 over 2 times negative 1. Okay, so that's negative 4 over negative 2 Negative 4 divided by negative 2 is positive 2. Okay, so that is the x value. Then we have to find the y value. To find the y value, simply take the x value and substitute it into the original equation, and that would give you the value of y. Okay, so you can check out what that is on our calculator. Okay, f of 2 is 9. So that point B they were asking for is 2 and 9, and that's our answer. Okay, moving on to the next question. The next question, 6.2, says, show that the equation of the line through A and C is given by this. So through A and C. Okay, so it's going to pass through A and pass through C. So the only thing we need is we just need the point of A. We already have C. And then it's really just finding the equation of a straight line. So how can we find the point A? Well, it lies on the graph of F, which we have. It's specifically the x-intercept. It's one of the x-intercepts. So find the x-intercept and we'll know what A is. To find the x-intercept, you simply make y equal to 0. So we're saying f of x is equal to negative x squared plus 4x plus 5. And then make y equal to 0. Negative x, I'm just going to say 0 here. And then you can choose to multiply by negative 1 on both sides, but I'll just see it as taking everything over. So it's now positive x squared minus 4x and minus 5 is equal to 0. Then let's go ahead and factorize. So we've got x, and then we need factors of negative 5 that can give us a 4. 5 is a prime number, so 1 and 5 are your factors. And then we need this to stay negative. Remember, one of it needs to be negative so that it can become negative 5. So we can give the negatives to the 5. So 1 minus 5 is negative 4. So that works out perfectly. So that is positive 1 and negative 5. And then solve for x. X is therefore equal to negative 1, or x is equal to positive 5. Okay, now we need to find A, right? We're not looking for the other one, just A. So which one would be A, negative 1 or positive 5? It would be negative 1, because you see where A is? It is on the negative part of the x-axis. So the coordinates, because it's an x-intercept, it will be negative 1 and 0. So we already know what that is, negative 1 and 0. And we can use these 2 points now to find the equation of this line G. Okay, let's go ahead and find it. So we're working with the point A, negative 1 and 0, and the point C, which was 3 and 8. So C is 3 and 8. So first you can find the gradient, and the gradient is y2 minus y1 over x2 minus x1, which is equal to, and let's just subtract. So that's 8 minus 0 over 3 minus negative 1, which becomes a plus 1. So that is really just 8 over 4, which is 2. 8 divided by 4 is 2. So our gradient is 2. And now we can find the equation of that line. I'll just use the quick method. There's the y equals mx plus c, but I'll just use this formula. Y minus y1 is equal to m times x minus x1. So we're saying y minus, now the y1 and the x1, they just stand for a point on your graph. So I'll take the easy point, which is A. A is an easy point, negative 1 and 0. So that's your x1 and that's your y1. So y minus 0 is equal to, our gradient is 2, times x minus negative 1, which becomes a plus 1. And so y minus 0 is still y, which is equal to, distribute, that is 2x plus 2. So therefore, g of x is equal to 2x plus 2, like they said it was. Okay, so that is it for 6.2. Moving on to the next question. Then question 6.3 says, calculate the maximum length of EH for where F is greater than G. So when they say this, they're really just telling you where the graphs are and what you need to really subtract. So if they're saying F is greater than G, it just means that we're going to make sure that this is where the graph of F is above the graph of G. And you can see it happens here. So here, the graph of F is above the graph of G. But everywhere else, as you can see, look at F, it's below the graph of G. Okay, so we just know it's this side. And they really just want us to find, they say the maximum length. Okay, that's not bad. Maximum length. So them saying f is greater than g is just telling us which one to subtract first. So this could have been seen as f of x is greater than g of x. See, if you take g over, they're really telling you to say f of x minus g of x. And you know that it's f of x minus g of x because they said f was greater than g, meaning f needs to be above g. Subtract these two graphs where f is above g. So f of x minus g of x. That's what we'll say. We know what f of x is, negative x squared. And then, so we're going to say that is negative x squared and then plus 4x plus 5. Okay. And we're going to subtract that by g, which we just got. Remember, that's to find the length of EH. That's how we're going to find the length, by saying that graph minus that graph. See them as y values. This y value minus this y value would give you the length of EH. Okay, so that's really what we're doing there. So EH is equal to this, and then minus g of x, we already found that to be 2x plus 2. So you can say minus 2x plus 2. And then, of course, when we distribute, you will see what that becomes. So this is the length of EH, first of all. The EH is equal to negative x squared plus 4x plus 5 minus 2x minus 2. Let's just simplify further. So EH is equal to x squared, and then those two go together and they become positive 2x. Those two go together and they become positive 3. Negative x squared, sorry about that. Okay, so that's a very important point there. Now, they want you to find the maximum length. This is the length only. This is the length of EH. But now we need to find the maximum length. So see it like this. The length of EH creates a parabola, specifically a concave down parabola. If you have to find the maximum value of this, the maximum length, okay, then you're really just trying to find the point at which it is at a maximum. It is only going to be at a maximum at the turning point, because at the turning point, this is the highest y value you can get for this graph. So that is the y value we're actually looking for. That value will tell you the maximum length of the graph, because the length is being defined by this parabola or this function. Okay, so how can we actually find that highest point? Okay? Since we know it's the turning point and the y value is really the y value of your turning point, which we usually call q. So to find that, we first need to find the x value. So how do we find the x value? Well, we already did this. How do you find the x value of the turning point of a function? If you're given the function in standard form, you use the formula x is equal to negative b over 2a. Okay, so that is going to be x is equal to negative, and our b value is 2 over 2. Our a value is negative 1. So that gives you x is equal to, that's negative 2 over negative 2, which is positive 1. So x is equal to 1. Right? That is the x value, not the y value yet. So we just found the x value. So how will we find the y value at which it is at a maximum? That would be the maximum value, of course, we're looking for. You take the x value and you substitute it into the equation of EH, and it will give you the y value, which is your maximum value. So EH is equal to, we say negative x, and in place of x we say 1 all squared plus 2 times 1 plus 3. Okay, this one is something we can actually just calculate. That's 2 plus 3, which is 5, and then this becomes minus 1. 5 minus 1 is 4. So the maximum length is 4 units, and we can just conclude, of course. Okay, so the maximum length of EH is 4 units. Moving on to the next question. The next question, 6.4, that's the last question for functions. And it says, given k of x is equal to f of x plus m, which is equal to negative x squared, and then minus, okay, a lot going on there. They want us to determine the value of m. First of all, k of x is equal to f of x plus m. This is being shifted. M is not a variable. Well, it's a variable right now, but it's actually stands for a number. Okay, it is being put here as a number. There's some sort of shift going on. Now, you know that when a shift is affecting the x value, what it means is that this graph is either being shifted to the left or the right. If it's shifted to the left, right, our m value would be positive, and then if it's the right, it's going to be negative. Okay, so just a back story on that. Then they tell us when they do this, it gives us this entire thing. Yeah, I feel like we can put this in some sort of a standard form, because what I'm trying to think about is don't get intimidated by the m. It's just a constant. That's what I keep telling myself. It's just a constant. So we can actually put it in standard form. Okay, but the question is, determine the value of m such that g is a tangent to k. That seems like the main point here. So what is the value of m so that g becomes a tangent to k? I've spoken about this whole thing with something being a tangent in my past videos as well. When you think about something being a tangent to another thing, they're really just trying to hint to you that their gradients are the same. That's really it. Okay, if you ever got lost there and you start seeing they said something is a tangent to another thing, they're really just telling you the gradients are the same. And if the gradients are the same, it means when you derive them, their gradients should be the same. That's kind of the main point here. But of course, I still want to understand it like graph-wise, just in case there may be anything we need to actually look at. So let me bring the graph down. Also, let me just see, when we're saying that something is a tangent to another thing, the reason their gradients are the same is because the only way something can be a tangent, or a line can be a tangent to a curve, is like that, okay? And at that point of contact, their gradients would be exactly the same, okay? Okay, so here's our graph. First, want to understand it logically before we start working on the algebra of it, because definitely there's algebra. This thing is for 5 marks, so it's not something we can solve by just observing. They would never give you all of this so that you can just observe, okay? So let's just try to understand it first, looking at it with the graph, and then we can go into the algebra of it. So determine the value of m, okay, such that g is a tangent to k. Currently, the graph that we have is f. And they told you how this graph of k gets formed. K gets formed by taking f and translating it. So we either shift it to the left or shift it to the right somehow. Okay. So, and then when it gets shifted, it becomes, g becomes a tangent to that graph. So I'm going to actually just draw the outline of this graph just so that we can like control it more and just see where it goes. Okay, so that's what we have there. What they're telling us to do is this graph is going to shift. Now it could shift to the left, but as I shift it to the left, I start to realize how much of a bad idea this is. This will never ever be a tangent to G. Do you see? It's always just going to intersect G like that at 2 places, here and here, because that's going to extend down and it's going to eventually meet that one. So it's a bad idea to shift the graph to the left. So the only thing we can do is actually shift it to the right. Okay, so we shift it to the right and eventually it will be a tangent. Do you see how it is touching? Now, of course, the diagrams are not necessarily drawn to scale. So I can't just go, oh, it's a tangent here. I don't know yet. I have to find out. Okay, so that's basically what they're saying happens. Graph of K gets translated. Clearly, it's been shifted to the right. And then it becomes a tangent to the graph of G. Okay, let's get into the algebra of this. How can we do that? Remember that the main idea is for something to be a tangent, a line to be a tangent to a curve, their gradients must be the same. Let us focus on finding their gradients, in other words, the derivative of each graph. So we can start with G, simple one. G of x is equal to, they told us what G of x was. G of x was, okay, 2x minus 2x plus 2. Let me not get that wrong. So 2x plus 2. And if you find the gradient of this, it's going to be, so derive, that's 2 times 1 is just 2. And then the x is going to fall away, of course, because 1 minus 1 is 0. Anything to the power of 0 is 1. 2 times 1 is 2. Okay, so that's what that becomes. Then let's look at the graph of K, because we need to find the derivative of K. So let's look at the graph of K. Funny looking graph, but don't get intimidated by the m's. The m's are just constants. They're just normal numbers. They're not variables. So let me just rewrite k of x first. However, they did say it's f of x plus m, and then they expanded it. Okay, so I'll just write the expansion here. Okay, so this is what we have. Again, don't get intimidated by the m. So it's still a parabola, just doesn't look like one, because you see that the highest exponent is 2. Highest exponent on x is 2. So all we have to do here is put it in its standard form. So in its standard form, it will be in the form of ax squared plus bx plus c. Let us just put everything that has x squared together, everything that has x together, and anything that is a constant together. So the only thing with x squared is this right now. So we can just rewrite that. So negative x squared. Then we need everything with x. Do you see that this has an x? This also has an x. So we can write them together. Negative 2mx and then plus 4x. And then everything else is a constant. Even if it has m is just a number. So minus m squared plus 4m plus 5. Okay, so we're still trying to put it in standard form, just in a way that we can easily see what these coefficients are. So it's equal to negative x squared. There's nothing we can do about that. A is just negative 1. That's all we can do there. But then what can we do here? Okay, so the whole point is I just want to see what the coefficient is, because if I'm able to do that, I'll be able to derive it. The whole goal is to derive k prime of x. So let us just get x on its own. Okay, so to get x on its own, I'll just take x out as a common factor. So I'll say plus x, and what is left is here in the first term with x, we have negative 2m that is left. And then in the second term with x, we have only positive 4. Okay, so there. Now I know exactly what the coefficient of x is, which is b. And then c is just everything else without x, because that will be considered as the constant. So that is just the negative m squared plus 4m plus 5. That is c. Okay, everything looks fine now. So now we just have to derive that. So this is k of x. Okay, so let's derive. So k prime of x is equal to, and the whole point is you take the coefficient times the exponent, which is going to be negative 2, and then leave the exponent, and then exponent minus 1, which is 1, and you don't have to rewrite that. Then in the next one, again, this is your coefficient, and you can see your exponent here. Maybe I should have written it the other way around, but okay, that's still coefficient, this, and then the exponent is what is on top of x. Okay, so it is negative 2m plus 4 multiplied by the exponent of 1 that we cannot see. So that stays negative 2m plus 4. And then if you still had your x, it would be, it's raised to the power of 1, right? You'd subtract a 1 from it and it becomes 0. X to the power of 0 is 1. 1 times anything stays the same. So that's what we have. And then what happens when you derive a constant? It falls away, and that's what's going to happen to that part. Because m may look like a variable, but it stands for a number. It stands for that f of x plus m, that number that shifted the graph of f. So we can just cancel it. Okay, is there anything that we need to add here? No. Okay, so this is fine. This is what we have. And remember, the whole goal is to find out where are the gradients the same, because the gradients are the same. If the gradients are the same, then that's where it is a tangent. So we're going to say g prime of x is equal to k prime of x. And we can just equate. So that one is 2. So this one is 2 is equal to negative 2x minus 2m plus 4. We need to solve for m. That's the whole goal. So let's just take that over, and becomes positive 2m is equal to, and here this is negative 2x, this is a 4, okay, so we have a positive 4, and we're taking this 2 over and becomes a minus 2. 4 minus 2 is positive 2. Okay, still need to solve for m. You can divide both sides by 2 to get m on its own, and m is equal to, so that's going to give you negative x plus 1. negative x plus 1, which I will just leave as 1 minus x. Okay, so it's still the same thing, positive 1, negative x. Okay, so that's what we have for m. Now, let's just see what other information can we actually use to find this. And it has to relate to what we have, the fact that g is a tangent to k, so it must still be that. Well, because it's going to be a tangent, I know I just put it here now. I don't know where it is a tangent. I can't assume anything. Because it is here, if it is a tangent, right, to the graph of k, then it means that the graph of g and the graph of k, that at some point they're intersecting, meaning at some point they're equal. Their x and y value are exactly the same. So why don't we use that? So with that being said, we can actually make g of x equal to k of x. Okay, so that's, and the reason I'm going to do that is because you see here, this is not very helpful. M is equal to 1 minus x. You still have two variables missing. So we need one more piece of information. Okay, so let's go ahead and equate g of x with k of x. So we're saying that g of x is equal to k of x, and this is just going to be a very long equation. In fact, I'm starting to think about it now. If I am equating these two, the goal would be, well, let's just start and then we'll see. I really think x should be the subject here, but we'll see. Okay, so we're equating these two together, and then let's go. So g of x, remember, is 2x plus 2. And then k of x is that long thing. And right now, I don't think it will help to take the factorized version of it, because you see things are going to have to go over and things like that. So that's just going to make us have to start breaking open brackets. So let's just take that entire thing first. Okay, so let's go ahead and equate. So we have, first of all, we can take x squared over just to make it positive. So x squared, negative x squared is over, and I'll just cancel when I'm done. So because there's a lot of variables here. So that's done, and it's the only thing with x squared. Now we can start with things with x. So there's still the positive 2x that is on the right hand side, and we're done with that one. Then there's this 4x. We're going to bring that over and it becomes minus 4x. And then there's this, of course, with the x as well. And so we're bringing that over and becomes positive 2mx. And then everything else is really just the constants with the m's as well. So that is this negative m squared comes over and becomes a positive m squared. That comes over and becomes a minus 4m. And we're done with that. And then our constants. Remember that on the right hand side, we already have a positive 2. So positive 2. And then this 5 that we have here comes over and becomes a negative 5. So minus 5 and then is equal to 0. Because everything has been brought over to the left hand side. So the left. Okay. So let's simplify. We have x squared. Those can already subtract. So that's going to give you negative 2x. And then still plus 2mx, will factorize if need be. And then plus m squared minus 4m. And then 2 minus 5 is negative 3 is equal to 0. Okay, so at this point, let me pause and just think about this. You see, the thing about this is we're trying to solve for m. If you want to solve for m, you need to substitute a value in place of x. So it means that this equation has to change so that x is the subject. So we're going to take this x over. So that was just me. Should have actually thought about that. And then it's 1, and then the m comes over and it's minus m. So we have 1 minus m. X is equal to 1 minus m. This is kind of like our equation 1. Okay. And then this is our second equation. And we're really just, working on that now. So what we can do here, if we don't need to simplify any further, we can simply just substitute the value of x into this equation. Okay, so we can do that. Let's substitute wherever you see x, we're going to put 1 minus m. So there's x squared. That's 1 minus m squared. And then we have minus 2x. That's again the 1 minus m. And then again, we have plus 2m times x. That's 1 minus m. And you see the whole point is to get everything to say m. Really just solve for m. And then we have plus m squared minus 4m minus 3 is equal to 0. Okay, so let us distribute here. So that's really just these two. They're the same thing. So you can rewrite it twice, but it's unnecessary. Square the first term, it's 1. Square the last term, which is m squared. And then first term times second term is negative m. Then times 2 is negative 2m. So we have plus m squared. Okay. Then distribute here. That is negative 2 distributes. It's positive 2m. Keep going. We're going to distribute here. That's positive 2m again. And that's going to give you negative 2m squared plus m squared minus 4m minus 3 equals 0. Okay. And then let's bring everything with m squared together. So this goes with this and this. But here's the thing. Okay, we can just add it. See, if you say m squared plus m squared, it gives you 2m squared. Then that's going to subtract with the 2m squared. So you see that they will cancel. So that's gone. And then we're only left with the m's and the constants. So that is a negative 2m and a plus 2m. Those would cancel. We're done with that. And then here we have 2m minus 4m. So 2m minus 4m is negative 2m. And now let's just deal with all our constants. We have a 1, minus 2, and then a negative 3. 1 minus 2 is negative 1. Negative 1 minus 3 is negative 4. Okay, so we have minus 4 is equal to 0. And then we have negative 2m, and we can take that negative 4 over, then divide both sides by negative 2, and therefore m is equal to negative 2. There's our value for m. So the question was, remember, determine the value of m such that g becomes a tangent to k. Okay, so the whole idea I used was the fact that if they're tangents, their gradients are exactly the same, but also if they're tangents, they are touching at that point of contact over there. Okay, so they're equal. So yeah, it's a long one, something that you really just have to focus so that you don't like make a mistake here and there. But that's what I get. M is equal to negative 2. Hi again, grade 12s. Okay, I noticed that this last question, there was actually a very quick way of doing this. So I saw that while editing this video. You see, because this, and the thing is I already said it, but the problem is I started with this whole g prime should be equal to k prime. We actually didn't need to do that. What we could have done is actually start from here, right? Make g of x equal to k of x, since at this point of tangency, they intersect, right? So because of that, we could have already said g of x is equal to k of x. And then at the end, when we get to this point, instead of substituting this point, okay, instead of substituting a value for x, what we could have done is actually first put it in standard form, just like I did with when deriving, the way I structured it here, okay, so that it has an a, b, and a c value. And then we could have just used the discriminant. So we could have actually said, because we need this to have a point of intersection, okay, a tangent. So for that to happen, remember that tangents only cut a graph at one point. So you want one intercept or one solution, really. So to do that, you make delta equal to 0, because this will give you equal roots. Equal roots really just means it's the same root. See, it's like this. X is still equal to 3 in this case. So you would make delta, or the discriminant, equal to 0. And then you have b squared minus 4ac is equal to 0. And then you would have substituted your b value minus 4, and then your a and your c, and that would have become an equation where you can actually solve for m, because there would be no x in this equation. Okay, so you guys can actually try that and see if you arrive at the same answer. Okay, so that's it for that part. Okay, so that is it for the function section of this paper, and I'll see you guys in financial maths.